This is John McGuire, and you are listening to the Qniverse podcast. Let me just say, before we get started, that today's episode is being brought to you in part by coldfusionnow.org, who helped facilitate the dialogue you are about to listen to. I hope very much that you enjoy it.
Today I have with me Dr. Melvin Miles. Dr. Miles is an electrochemist and college professor who earned his PhD from the University of Utah. Now retired, he spent much of his career at the China Lake Naval Research Laboratory, and is probably best known for systematically detecting the presence of helium ash in Palladium-Deuterium cold fusion cells between the years 1989 and 1995. Many experts in the field believe that Dr. Miles' findings constitute some of the best evidence in favor of the cold fusion hypothesis. Dr. Miles, thank you so much for being with me.
Okay, thank you.
Before we proceed, can you first tell us a little bit more about your background, your credentials, and how you got involved in the field of cold fusion?
Right, okay. Well, I want to go back to the beginning. I grew up in southern Utah, St. George, Utah, and being a Mormon community back then, it was 99% LDS or Mormon. Like a lot of other people, I went on a church mission to Germany, and that was after I had 2 years at Dixie College, which is located also in St. George. And so I was in Germany from 1957 to 1960. So I learned to speak German quite well, which came in handy sometimes. And when I came back, I attended Brigham Young University. That was in 1960 to 1962. And I got a BA degree. It's a BA because I knew German. I took German classes, so BA means Bachelor of Arts instead of BS, Bachelor of Science, because of the German knowledge I had. And I got a degree at BYU in chemistry in 1962. And then I moved up 50 miles to the north of Provo, Utah, to Salt Lake City, Utah, University of Utah. And there I began my work on a PhD in 1962. And I actually finished that work up in 1965. But I worked some with Henry Eyring, who was real famous in reaction kinetics, and that I did most of my work with his son, Ted Eyring, in temperature jump kinetic studies. And I completed all the work in 1965, but I didn't get the degree until 1966, because it was already September. And then I went on a NATO postdoctoral fellowship to Germany, Munich, Germany. Henry Eyring knew Heinz Gerscher, and that's who I worked for. He was a famous electrochemist. He was president of the International Electrochemical Society at one point. And I did a postdoc with him starting in October of 1965 till October 1966. And that's where I really got into electrochemistry, was with Dr. Gerscher. And electrochemistry is just another way to do kinetics. So current is the measure of the rate of the reaction taking place at the surface. So still kinetics in a lot of sense. So that's one reason I enjoyed it. But incidentally, Heinz Gerscher went to the second cold fusion conference in Como, Italy. And he was rather convinced by what he saw there, and he tried to get people in Germany interested in cold fusion, and he wrote some letters about it. And he was quite influential. He was working for the Max Planck Institute at that time. I think he was looked at as the president or leader of the Max Planck Institute in Berlin, Germany. But anyway, that's where I got in electrochemistry. Then I came back to the United States in 66 and started to work for the Navy, the Naval Ordnance Laboratory in Corona, California. That's near Riverside, sort of in between Riverside and LA. And I worked there for 2 years, 1967, 1969. When it became part of China Lake, and some groups are not invited to move to China Lake, my group was one of them. So then I went into teaching at Middle Tennessee State University in Tennessee, near Nashville, Murfreesboro. And I taught chemistry there, physical chemistry, from 1969 to 1978. But in the summers, I'd go to China Lake to do research, or I'd go to Brookhaven National Laboratory in Long Island, New York, to do research. So almost every summer, I was off doing research. And eventually, actually, both places wanted to hire me in 1978. And I chose to go to China Lake because I like the West, I like California. So I went there I had a leave of absence from the university just in case things didn't work out. But that started my career with the Navy. I did mostly research on thermal batteries, electrochemistry, and corrosion, and some other projects at the time. So that was my background up to the time about when cold fusion announcement came out. And I think part of your question was how I got involved in the field of cold fusion. I didn't hear the announcement on the first day, but the second day, I think I was driving to work and I heard it on the radio. It was discussed on the radio. And I got in there into work and I started thinking I could really do that experiment because I was already working with palladium and hydrogen. I used that as a reference electrode, low palladium electrode with hydrogen. That makes it a good reference electrode, particularly in non-aqueous solutions, which is what I was working with. And I had heavy water just across the hall in the nuclear magnetic resonance instrument room. They used a lot of heavy water, as they usually do for NMR. And so I had everything I needed right there in the lab, so I started work that weekend. I started my first experiments. But like a lot of people, I didn't know really how to do the experiments. I just trying whatever I thought might work, and it was not very good. But that's where I started, was that weekend of the announcement. And I had a postdoc working with me. He became very interested in it, David Stilwell, and he had more freedom than I did to work on it. I had projects that were funded I needed to work on, and so he did a lot of the early work and designing calorimeters. We tried one after another, and each one is getting a little better until we finally could do decent calorimetry work. But for the first 6 months, we never saw any excess heat. We got to where we could measure about exactly the same heat coming out as the heat going in. I think our result, the ratio of heat out, heat in was 1.00 plus or minus 0.04. So within 4%, plus or minus 4%. It was the best we could do. And while all the controversy was going on and groups were claiming they'd seen something or other groups claiming they saw nothing, I was just one experiment after another getting zero excess heat for the first 6 months of work I was doing. That's how I got started.
As I already mentioned, and we've discussed a little bit already now, between 1989 and 1995, you carried out a series of experiments that sought to identify nuclear products in Palladium-Deuterium electrolytic systems, namely Helium-4 ash. So if at all possible, can you summarize this body of work that seems to demonstrate a strong correlation between excess heat and helium production?
First, let me explain how I first got excess heat. The palladium that I was using was what was already in the laboratory, and I later found that the loading was very poor. It didn't really load deuterium very well, and so I could have done 100 experiments, probably never gotten excess heat with that particular palladium. And it was only when I got a different order of palladium in, made by Johnson Matthey. It was actually a thick rod, about 6 millimeters thickness, so it was a much bigger volume, and I think that made a difference. And also it was made by Johnson Matthey. And when I started using that material in every experiment I did, started producing excess heat. So right off, that shows that the material was the key factor. You had to have the right kind of palladium that could, for some reason, load properly in order to get the excess heat effect. Also, I think, in thinking back, you need a large volume. A lot of people still like to say it's a surface effect, and I think it probably is a surface effect, but I think the volume of the palladium is important because in my experience, the larger the volume of the palladium, the larger was the excess heat. So somehow the volume comes into play as well. And this new Johnson Matthey palladium had a 6 millimeter diameter and about 2 centimeters length. That a rather large volume, and I got some of the largest excess heat effects I ever saw was with this palladium. And it was also about the biggest volume of electrode that I ever used. And so the first excess heat experiments were late in 1989. I was getting calls from the Department of Energy, ERAB people, asking me if I'd seen excess heat. And all summer long, I told them no. And finally, in September, I let them know that I had seen it finally. But when that report came out, the well-known ERAB DOE report, I was still listed with Caltech and Harwell and MIT was a group, the China Lake group, reporting no excess heat. I think I was the only person I know of that at first had no excess heat and then later had excess heat. And that's why I was sort of, in the ERAB report, I was listed with a group with no excess heat. But then the experiments were producing excess heat about every time. When I first thought of doing the helium study in the experiment in 1990, I contacted Ben Bush, or he contacted me. He wanted to come to China Lake as a postdoc and work with me. It turned out he was an expert in keeping air out of samples, working within an air-free environment. and keeping air from getting in, and that came in very handy. Because with his help, we designed how we could do the experiment and keep air out. I mean, you can't keep it all out, but you can keep most of it out. You keep it under positive pressure, and there's no leaks really. There's just the gases coming off go through an oil bubbler, so air can't backflow in. The only way air could get in is through glass, and we later found that's too slow to make much of a difference. That was a big criticism, that air could leak in, not really leak in, but could diffuse in. And helium at least could diffuse in. Helium being a very small molecule, it could go through little spaces in the glass and gradually make its way into the container. And that was major criticism, not that we had a leak, but that helium from the air could diffuse through the glass and get in the system. And that was the early criticism. When we reported, we found heat and helium. Now, that first study with Penn Bush, with his help of how to flush the system out with boil-off nitrogen, which doesn't have any helium. We tested, there's no helium in it, and there couldn't be because helium would boil off way before anything else like nitrogen. And so we backflushed with the boil-off nitrogen and then let the system run for a little while and then collect a sample in a 500 milliliter glass flask all the time under positive pressure because the gases were flowing through the oil bubbler, and that created a little positive pressure inside. So if there's any leak, it would have been the flow outward, not inward. But like I said, I don't think they're any leaks. They're just the possibility of helium in the air diffusing through glass into the system. But of those first experiments, we didn't have NMR at China Lake that could do the helium analysis, so I sent the samples off to Penn Bush at the University of Texas. That's where he was located. And he enlisted the NMR person there to run the analysis. And I think of that first set, we had 8 out of 9 that gave excess heat, showed excess of helium-4. Helium-4 showed up in the mass spec. And just to make sure it wasn't leaking in, we ran 6 controls in regular water where there was no excess heat, and he found no helium in the mass spec studies showed no helium getting into those samples. So the background, we were able to keep the background out based on the controls. 6 out of 6, no heat, no helium. 8 out of 9, heat and helium. The one exception was probably calorimetric error, but I've left it in. You just can't arbitrarily throw data out. You've got to leave it in. You can explain it away maybe, but you still keep it in. And so that was the first set. 15 experiments, 8 showing heat and helium, 6 showing no heat, no helium, and 1 showing heat, but we did not find helium. 1 was outside what we would have liked. Then that's when all the controversy came up. I presented these results at the Como meeting in Italy. In Como, Italy, that's Heinz Gerscher, my person who did the postdoc, was there at the meeting, so it was good to see him again. So he heard my presentation and other presentations and became convinced something real was happening in the field and tried to enlist Germany to get involved in it, but I guess he didn't get very far with that. But after the first set of experiments, Brian Oliver and another person from Rockwell came up from LA area. He worked for Rockwell at the time, named Brian Oliver. He wanted to analyze our flask and study the rate of helium from the air getting in, and this we did, and found that the rate of helium coming in was too slow to affect our results that we reported on the first set. And we also found that if the flask is filled with deuterium, then deuterium can also diffuse through glass. Deuterium inside is diffusing outward, and helium from the air is diffusing inward. And even at the meeting in Como, I proposed that because deuterium was inside the flask diffusing outward, it would impede the helium in the air diffusing inward. And it turned out I was correct. It's about a factor of 3. It makes about a factor of 3 difference if you have deuterium inside the flask than if you have, say, nitrogen inside the flask. The rate is very definitely different of helium from the air diffusing in if deuterium is diffusing out and it impedes the progress of helium. But anyway, with Brian Oliver, he wanted us to get excess heat again and then send the analysis to him. But the rest of that time period, we had trouble getting excess heat. It was a frustrating area to work in. I went long periods sometimes with no heat at all being measured. It wasn't until the end of that year that I got heat again, we collected 3 flasks and sent them to Brian Oliver at Rockwell. And he measured the helium as a function of time, day after day, for about 40, 50, 60 days. And you could get a straight line. The helium from the air was diffusing in, but it was a straight line. It was linear over time. And you could extrapolate back to when the flask was taken off the experiment and sealed up. And he reported very accurate results of how much helium was there initially in terms of 0.01 parts per billion. So we measure, like you mentioned, parts per billion, but he was determining the helium in terms of 0.01 parts per billion. So the measurement was quite accurate. To measure parts per billion when your air is plus or minus 0.01 parts per billion. And this was some of the best results I ever got. This was a double-blind experiment. I never knew what the helium results were, and Brian Oliver never knew which flask produced more excess heat than the others until we both sent the results off to a third party. This was Professor Legasky at the University of Texas, and therefore neither one of us had a chance to change data, even if we wanted to. Of course, I wouldn't want to, but couldn't do it anyway, and those results turned out to be some of the most accurate results that I have on the relationship of heat and helium. In fact, I recently posted on the discussion group a short note about those 3 studies with Brian Oliver doing the accurate helium measurements, probably the most accurate that anybody in the world could have done at that time. So that was the second set. 3 experiments gave excess heat. All 3 showed excess helium. And the one with the largest excess heat gave the most helium. The one with the smallest excess heat gave the smaller amount of helium. So they're in the right range. More heat, I got more helium in those experiments. And that was the second set. So 3 out of 3 produced heat and showed excess helium production. And then the third set, because there's still controversy, we went to the all-metal flask, and it's well known that helium does not diffuse through metal. And so we designed and made metal flasks with a metal-to-metal seal, so there's no place that the helium could diffuse through. When you close the flask off, it was a metal-to-metal seal where helium could not diffuse in or out. And by this time, we found another group to do the analysis, the third group, and this was in Amarillo, Texas. They were also experts in measuring helium because Amarillo, Texas, if you drive through there on I-40, you can see that there used to be at least a sign that called it the helium capital of the world. Most of the helium in the United States is located there in the trapping oil wells in the Amarillo, Texas area. And this was a government laboratory, Department of the Interior at the time, and they did routine helium analysis. That's full-time work that they did. They were experts in it. So we sent the metal flask off to this DOI laboratory in Amarillo, Texas, and this was the third set. 9 experiments showed excess heat in the metal flask, and all these 7 showed helium. So we had 7 out of 9 that correlated with the heat and helium. 2 did not. But the 2 were very different cathodes. They were palladium-cerium cathodes. And I don't know to this day whether, because you have a palladium-cerium alloy, whether the helium gets trapped in the palladium or somehow it doesn't get out like it normally would. So I could almost make an exception to those 2 that they were not pure palladium, they were palladium-cerium. And then we had 6 experiments that produced no excess heat. All 6 of those experiments showed only background levels of helium. By this time, we knew quite well what the background was, so I could always subtract the background off and do a calculation. The background was, I've given it the places. I'm trying to think of what it is right now, but it was pretty small. It was somewhere around 4 parts per billion, and I was measuring up to 9 or 10 parts per billion. And the background was very, very consistent. It was always about the same in the experiments that I was doing. And so I think that you can make a good case that we were very consistent on the background amount when there's no excess heat. In terms of atoms, it was 0.51 times 10 to the 14th atoms. People get worried about parts per billion, but that's still a lot of atoms. That might have been 4.6 parts per billion in the background, but it was 0.51 times 10 to the 14th atoms of helium per 500 milliliters in the flask. So still a huge number. So parts per billion is not as tiny as you think if you express it in terms of atoms that you're measuring. But anyway, we were well above that in the class that showed excess heat, and I was always able to calculate the amount of helium produced per second per watt. That's a figure quite well known in nuclear physics. If you have D plus D fusion, that should be around 2.6 times 10 to the 11th. And my measurements are always close to that, but less. And it's less probably because probably all the helium doesn't get released from the palladium, so it probably would be less. Some people say it would be only about half, because half might go off in the direction and get embedded in the palladium, and the half will come out of the palladium. But my results would range around 1 or 2 times 10 to the 11 helium atoms per second per watt, which is close to what you would expect. Not exactly, but I wouldn't expect it to be exactly, because for several reasons. Is D plus D the only reaction? I'm not sure. Could be other reactions that contribute, and therefore it could be less because of that. It could be less because all the helium doesn't escape completely from the palladium unless you agitate it like Mercury did and eventually get it all out. It doesn't all come out all at once. It doesn't necessarily all come out during the experiment, and so it may stay trapped for a while inside the palladium. So I think I'm quite satisfied with the results that I got in those cases. That was 3 sets of experiments. 3 different groups did the analysis. All 3 sets agreed pretty much. If you saw excess heat, then you found helium. If you did not see excess heat, you did not find helium, or none above background at least. And I think statistically, 18 out of 21 that showed heat also showed helium. Only 3 exceptions, and 3 exceptions could be readily explained. 1, the calorimetric error. 2 others for palladium-cerium instead of palladium. In the experiments that gave no excess heat, 12 experiments, all 12 did not show helium. So 12 out of 12 was we were perfect on the ones that did not produce excess heat. There's no helium produced. And I've done a calculation based on statistics, which I posted a few weeks ago also on the CMNS group, and the probability of getting those results by chance comes out to be about 1 chance in 750,000. Now, I doubt I could have been that lucky. It could have happened by chance. And I don't see how anybody else could think that would be reasonable either, that you'd get these results by chance 1 out of 750,000 times. And that's just based on the statistic calculations. But anyway, that's pretty much the background and the story of heat and helium. And I don't like the word leaking, because I don't ever think I had a leak in the cell. If I had a leak, you would have sent the mass spec off the scale. It would have been such a big effect. And the only way the helium got in is it could diffuse through glass, or maybe diffuse through connections that I had, thick rubber tubing. It was a likely source where some helium could diffuse through. But the background is quite reproducible when we got accurate enough that we could measure the background.
Right. To me personally, what's so interesting about the heat-helium work is that when Pons and Fleischmann first came out with this work, much of it was brushed aside based on the argument that, well, it can't be nuclear fusion, because they put forward faulty neutron data. They weren't experts in that, but they tried, and they presented it at kind of a half-baked conference and whatnot. So the data was not perfect, and they were basically skewered for doing that. And then for anyone to say, okay, well, it's fusion, suddenly got shouted down and said, well, the neutrons weren't there. But what's so interesting about the Helium-4 work is that this is expertly done experimentation to decipher what is the ash or the nuclear product that coincides or is quote-unquote commensurate with the excess heat that we see in these systems. Because neutrons, tritium, all these other nuclear products don't necessarily line up with the heat that's involved or that's measured and observed. So we're not talking about traditional fusion, but it very much seems that we have some kind of nuclear process going on, possibly fusion, because, again, once all the deuterium to helium is accounted for and the helium that is both flushed out and trapped, you get awfully close to that. I think it's 22 MeV for D plus D. But again, we don't have the gammas or anything to suggest that it's traditional D plus D, but it could be some kind of fusion based on what you're telling us here and have shown back in the early 90s, and then Makubri, of course, replicated, and you have other work, say Ania in Italy. Arata has done some heat helium work, but yours and Makubri's is often pointed to as the best. But often people just say, well, it can't be fusion because we know D plus D would give us gammas.
Let me just explain a few things. Of course, one thing a lot of the critics said was, if you're producing helium-4, where is that 23.8 MeV gamma? That was a big question mark. Well, they were trying to force cold fusion reactions to be the same as hot fusion reaction, and a Nobel Prize winner, Julian Schwinger, had already came out in 1989 and said that you could not expect cold fusion inside a metal lattice to be the same as hot fusion. But the critics were trying to force cold fusion to be the same as hot fusion. So if you formed helium-4, you had to have the 23.8 MeV gamma. And the answer is they're not the same. One is in a plasma where the atoms are pretty isolated. Two deuterium atoms come together under high temperature and high speed because of the temperature and get close enough for fusion to take place. In a metal lattice, you have all sorts of other things nearby. You have a lot of electrons, you have a lot of palladium atoms, you have a lot of deuterium atoms. They're all concentrated in space. Martin Fleischmann likes to sometimes refer to in terms of concentration. You have about a 500 molar concentration of electrons inside the palladium. It's definitely a very different environment. Many different things. Neutrons, the protons that make up the atoms, electrons, all there being forced together in the metal lattice. And so I'm not a theoretician, but I think you'd have to expect things would be quite different. And you don't get the 23.8 MeV gamma, but in fact, if that gamma were formed, it would leave the cell, it would probably leave the building, it would probably get energy be deposited maybe a half a block away or so. And so your calorimeter would not even be showing excess heat if the gamma was being produced, and it wouldn't be stopped by the cell. It would go a block away maybe through walls and so on. And so if you were producing the gamma, I wouldn't expect you to see the excess heat. And so the reactions are different. Hot fusion is one thing, cold fusion is another thing. And you can't really compare the two, which is what the critics were trying to do.
Right, I agree. And no matter what the mechanism ends up being in these systems, in palladium-deuterium or nickel-hydrogen, it's going to be something novel and something interesting that we missed. So I think all theories are taking a leap of faith, if not grounded in experiment. 1 in 750,000 is not too bad, you know?
And by the way, Martin Fleischmann in a letter to me, I'm presently working on a book that Ruby Carey's helping us. These all the letters that Martin Fleischmann wrote to me. I have a lot of letters from Martin Fleischmann over the years, starting around 1992. But in one letter, Martin Fleischmann mentions that he and Stan Pons saw evidence for helium-4 in 1988. The year before they even did the announcement, they saw evidence for helium-4. And they were considering announcing helium-4, but they decided they were getting so much criticism over what they'd already announced that they didn't want to open, as Martin said, a second front. So they didn't want to defend a second front from attacks. So they were about to report helium-4 results, but they decided not to in 1989. But they'd actually seen it in 1988.
I see. Yeah, I heard that either Pons or Fleischmann had handed over samples to be analyzed for helium, and some had been found, but at the same time, the way they actually tried to extract the helium seemed to suggest that they were missing a lot of it. Some is escaping in the gas.
These samples were palladium samples, so they were assuming that all the helium would be inside the palladium. If that were true, there would have been a lot there.
Right.
But my results, and also some of the theoreticians at the time, Scott Chubb and Talbot Chubb, are good friends of mine, and also very good theoreticians that are working for the Naval Research Laboratory. And even before I found helium-4, unknown to me, I didn't know about Scott Chubb's theory. I didn't even know who he was, really. But he had written a paper predicting helium-4 would be the product, and it would not be found in the palladium, but it would be found in the outgas, coming out of the experiment. And he was right on that prediction. And Preparata in Italy was also predicting helium-4 in his theory, his quantum electrodynamic theory, QED theory, that Martin Fleischmann particularly liked, the QED theory of Preparata. And Preparata also, prior to my experimental report, was predicting helium-4 as a product. So I give both those theoreticians fine credit for predicting something that was found a little bit later, not much later, but within a year later. And in fact, Preparata, because of my finding of helium-4, he made a trip to China Lake and visited my laboratory. That's when I first met him. We had a good discussion. He saw my experimental setup, and he thought it was important enough that he made a trip from Italy to visit and see the laboratory. Or maybe he's already here in the United States, I don't know, but he did visit the China Lake laboratory, which is not easy to do. You have to get clearance and notify people in advance because of the secret things that go on there. But he did get a clearance, and he did come in and visit China Lake laboratory at the time, shortly after we reported our results for helium-4. So anyway, I don't really think I was the first. I was probably the second. I would give Martin Fleischmann and Stan Pons the credit being the first to see helium-4 in cold fusion experiments. And McCruby and other people followed. McCruby, Rada, people in Italy. There's quite a few groups that have now found evidence for helium-4. And in my conversations with Martin, I know that the work that went on in France, in the south of France, that they did measure helium-4, and they probably have a lot of data on helium-4, but it's never been released. It's under the control of the Japanese. This work was funded by Toyota, but I think they had a lot of evidence for helium-4 and the comments that Martin made to me based on the work that was done in the south of France as well.
Right, because he and Stanley Pons went to France for a while and did some research. Is that correct? And they got some very interesting results, a lot of excess heat from what I remember.
Yeah, Stan Pons thinks he was more or less rudely shoved out of the science establishment in the U.S. He has some strong feelings about that. I've heard people who talked to Stan Pons said that he never wants to set foot in the U.S. again because of what happened. And his kids were going to school in Salt Lake City, and other kids at school were telling his kids, Stan Pons' kids, that your father is a fraud. We've heard your father's committed fraud, and so on. And so it just really made life terrible in what happened after the announcement in Salt Lake City.
Back in 1989, the negative results that came out of Caltech and MIT labs proved to be a major setback for cold fusion. Now, more recently, you took it upon yourself to write a peer-reviewed critique of these labs' methods and their procedures. So, again, could you summarize where exactly these labs went wrong and maybe the impact they had in and around the time of the announcement in your firsthand experience?
Okay. While I was working at China Lake, I did a lot of studies of their results, and I got a paper published in Journal of Physical Chemistry, one of the few positive papers that published on cold fusion, where I criticized the Caltech and the MIT calorimetry, point out errors that were made. And there were a lot of errors. In one of his letters, Fleischmann told me he's found a lot more errors than I did. We'll probably go into some of those in one of his letters in this book. But let me say first off, probably the first important thing is that they did not get to high enough loading to get excess heat. And the McCruby's pointed this out, and they reported their loading was around 0.7, 0.8, or maybe less. But they never got up to loading. You need loading about 0.85. That's the deuterium atoms to palladium atoms inside the palladium. You need to get that ratio up to about 0.85, preferably closer even than that, even maybe near 1. But neither Caltech nor MIT had the loading sufficient to expect excess heat from what we know now, what they reported. So that's one thing. The second thing, their calorimetry was very poor, and that's what I point out in this paper in Journal of Physical Chemistry of 1994, if anybody wants to look it up. 1994 paper, pages 1948, 1952, those are not years, those are pages. 1948 to 1952, published in 1994. A lot of things were wrong. First, they left out a lot of important calorimetric terms, and I've gone through that in some papers I've published. Second, Nate Lewis used a short, fat cell, and to get good stirring, his big argument was Fleischmann and Pons did not stir their cell properly. And based on Nate Lewis's cell, that cell would not be stirred properly. It's fat, a large diameter, and a short height. In order to get good stirring by electrolysis gases, you need a narrow cell, a small diameter, and a large height. And that's what the Fleischmann-Pons cell were like. I worked with them in Japan. The diameter was about 2.5 centimeters. That's only about 1 inch. That's the diameter of the cell inside. And it was about 25 centimeters in height. Nate Lewis' cell had a wide diameter, and he claimed to get good steering, he had to put a steering bar in it. Well, of course, with his design, he would have needed that. And the steering bar produces heat and makes uncertainty in the calorimetry. So his cell design was poor. It was not narrow and tall, it was short and fat. It's also the way he did the experiment. He assumed by changing the input power, he would change the excess heat. But if his excess heat stayed constant, he would have not seen anything. So that's another thing that I went into. It's more mathematical, so I can't really discuss it on the phone. But the way he did the experiment, he could only see anything if the excess heat had changed. He could not have seen anything if the excess heat stayed constant. And despite all this, he has a strange result, and I still don't know what to make of it. His regular water cell had a very steady cell constant, stayed the same. His heavy water cell, he had to keep changing the cell constant. There's no reason for the cell constant to change, but the only reason he reported zero excess power is that he kept making the cell constant larger. He used the cell constant inverted to what I use. I use watts per degree. He used degrees per watt. And so the largest cell constant would have calculated away the excess heat if he allowed it to change, which he did. In that paper, I did analysis. If we assumed his early cell constant was correct and it did not change, then he had an excess power of about 76 watts. And based on his volume of electrodes that he used, which was rather small, that comes out of around 1 watt per cubic centimeter. And this is exactly the guideline that Martin Fleischmann used. As a guideline, you should expect about 1 watt per cubic centimeter. I'm not saying that it's a volume effect, but a larger volume seems to give you a larger effect. I still think it could be a surface reaction, but the deuterium loaded inside the volume is also important. And I found in my experiments, I typically get about 1 watt per cubic centimeter of palladium. The Nate Lewis experiment where he changed the cell constant, if he didn't change the cell constant, his result also comes out about 1 watt per cubic centimeter. To start with, though, he didn't have high enough loading, but maybe when he measured the loading, it was low, but maybe later on it was high enough to get excess heat. So he may have had excess heat that he calculated away by changing the cell constant of the heavy water cell. He didn't need to do that with his light water, and he did not do it. So that's a very strange result, I thought, in the Caltech. Then moving on to MIT. MIT has gotten in a lot of controversy over the years because they came out with data and then they revised the data. The early data seemed to show some excess heat effect, and then they revised the data where they zeroed it out. Some people have already written a lot about that, and whether or not they had excess heat, I don't know. But if they did, it looks like they zeroed it out also for some reason, probably because they had the outcome already figured out. They already had a wait for cold fusion celebration to do away with cold fusion before they finished the experiment. So they were not objective. They had an agenda. Their agenda was there is no excess heat, and if you start off with an agenda like that, you don't do honest science. So I don't think their work was honest. That's my opinion. But a couple years ago, Peter Hagestein sent me further data on the MIT experiment that gave me information I didn't have before. And I found out that they had a very large layer of insulation around their cell. And I did some calculations based on that thick insulation around their cell. They would have forced most of the heat to go out the top rather than going through that insulation. You've got to be careful not to overuse insulation, which is what MIT did. But based on my analysis, which was published just a couple of years ago in the journal Condensed Matter Nuclear Science, the major heat pathway of the MIT calorimetry was not from the cell to the water vat, but it was from the cell out of the top into the room temperature. And the room temperature is not controlled that well, and that's a very poor pathway to try to do good calorimetry. And so I think for that reason their calorimetry was very poor. And there were other reasons as well, but some of these were mentioned in the paper that I published in Journal of Physical Chemistry. So anyway, that's the background to Caltech and MIT, and I think Martin Fleischmann had all the different terms that could affect the calorimetry worked out, and hardly any group used all these important terms. A lot of them left out critical terms in their calorimetry. They did not understand it as well as Martin Fleischmann and Stan Pons did, and they did not use the full calorimetric equation that Martin and Stan reported, and they left out important terms, and that also would lead to calorimetric errors as well.
So it's interesting that you just kind of brought up the political side of cold fusion, because that's certainly a big dynamic. And often we hear from people in the community that the rejection of cold fusion was and continues to be more politically motivated than it is fact-based. So why do you think LENR continues to be overlooked despite what seems to be a copious amount of experimental verification that has piled up over the years?
I think because the scientific method is not followed. You know, the scientific method, you don't use ridicule, and Caltech had an agenda at the Baltimore meeting in May of 1989. I was not at the meeting, but Charles Boudet in his book writes a good report of it. They had an agenda to kill it for some reason, and that's not the way you should treat new science. New science should be given time to be carefully explored and careful experiments to be done. And it takes time. It should have taken a matter of years before anybody could rule out that it was correct or incorrect, and that it needed time. And instead, Caltech, Steve Koonin and Nate Lewis of Caltech took it upon themselves to, with the press being there, to make a play to the press and to use ridicule and try to kill this field off. And they did a good job of it, apparently. And that's not the way new science should have been treated. It should have been given time for the scientific method to work, for people to do careful experiments. It took me 6 months before I saw anything. I could have got on a soapbox and denounced it, but that's not the way science should be done. I knew I hadn't explored all the possibilities. I'm sure Caltech had not either explored all the possibilities. I know they did not, and neither did MIT. It takes time to do check out all the different variables and all the different things that you should look at before you rule it out. But unfortunately, Caltech and MIT are apparently the leaders of the scientific community in the U.S. and the world. And when they came out with these negative statements and ridicule, more or less people just like sheep, they just fell in line and decided, well, this has been debunked, or this has been disproved. And so it just became purely political. At that time, the people had seen things already, like myself and Mike McCreery and others. We knew we had not made mistakes, so we continued. And we were still trying to find out and understand it better. And I think also early on, some people got embarrassed. I know of groups that they wanted to be on the bandwagon. They wanted to come out and make a press announcement right from the beginning and get publicity. Yes, they had reproduced the effect. But then they found out they did something wrong, and then they had the embarrassment of having to retract what they'd said. And I think they got angry because they prematurely said they had found something, and then they had to retract. And I think that made enemies as well.
Mm-hmm.
But it should have been done very carefully, very slowly, over a period of time. It should not have been hyped up so much, perhaps, in the news media, and it should have been more of a research topic for careful studies over a period of years instead of a period of a few months. MIT and Caltech tried to dismiss it within a matter of just a couple of months, which is far too short. And if you look at the history of science, this is not always unusual. Galileo, nobody accepted his finding with his telescope. The dominant church at the time, the Catholic Church, forced him to recant his findings, and later it turned out he was correct, but he had to recant what he was seeing through his telescope. And I guess they wanted Martin Fleischmann and Stan Pons to recant what they were seeing with their calorimeters, but they did not because they knew they were right. If I ever knew I was wrong, I would have said so, but I never have seen evidence that I was wrong. And so they all played into politics. The fact it could be a big energy supplier, future energy, to capture the fusion nets of the sun and the stars. The universe is powered by fusion energy. If we could capture here on Earth, that would be the answer to all our energy needs. And therefore, it was widely publicized. Any type of fusion, hot or cold, if it can be made successful, is a big topic for the people of this earth, because we need energy. And that is one of the best ways I can think of is to get it from fusion energy if we could do it. And so that made it very politically as well. But I think it was just poorly treated. Martin Fleischmann said that he was always surprised. In his letters that I spoke about in maybe a possible book, he said the attitude of the people was that you're wrong and you must stop. That was the attitude. You're wrong and you must stop this research. But that's not the way a new research topic should be approached. You should be, maybe you're right, maybe you're wrong. Let's look at it carefully over a period of years. That's what should have happened, but that did not happen. Only the people who had done research and saw something that we knew we had to continue because we could not retract what we knew was right, including Martin Fleischmann and Sam Pons. So that's what way I sum it up. This then can be very political, and most people you talk to, they have an opinion of cold fusion that, they'll say, wasn't that disproved? Wasn't that found to be wrong? If they know anything at all, that's what they remember. That was proved to be wrong, or that was not true, or that was incorrect. And that's a hard thing to overcome because that's what almost anybody you talk to, that's all they know.
Right. And in that book you mentioned, Excess Heat, which is a very important book that everyone should read, I think, that's interested in the subject matter. That overarching thesis that's hammered home again and again is, okay, you can pick apart the neutron data. Okay, you can create all this smoke and mirrors surrounding the tritium data, and was it spiked or not, even though storms clearly showed that it wasn't. But that's beside the point.
Now, what book are you referring to? Charles Boudet's book?
Yes, that's the one. And throughout that, he hammers home the point
about the history of this field. I'd recommend it to anybody.
Yes.
Who wants to know the truth of what happened.
Right. And I think what we all need to focus on is, okay, it's excess heat. It's kind of a black box at this point. We have some maybe ideas about what might be producing the heat, but as you mentioned, the calorimetry is complex. Electrochemistry is complex. These are not disciplines that a nuclear physicist can drop everything he's doing, having not worked in the lab for over a decade, and suddenly discover what Pons and Fleischmann did, who were basically masters of their area of science. So, the neutron data were red herrings in the face of the excess heat, which to this day is beyond question. As you've mentioned, the calorimetry and all the things that supposedly disprove excess heat, you can find error after error, whether it's loading or the way the calorimetry was done or the palladium was old or whatever their metal hydride is impure. So There's all kinds of factors that we're still figuring out, but we know enough to be able to identify good research from bad. Now, I guess a way maybe to bypass all the political noise, well, maybe we're not bypassing it, but in a way we're circumventing some issues by just going commercial with LENR. Obviously, we have people like Andrea Rossi or Brillouin, and they say that they're on the cusp of something. Now, obviously, you're an experimentalist first and foremost, but do you have any read of this situation? Do you have any opinion on how that's developing, and do you see any hope for it?
Yeah, I'm more familiar with Rossi. I keep hoping Rossi is correct, and I hope it can be commercialized, because that would be the quickest way to end the controversy, is come out with a commercial device that you could prove to people that it actually works, that it can be used to heat buildings and so on. And then they have no argument at that point.
Right.
So that's one way to end the controversy, and I hope that maybe will work out. Now Rossi, I know he uses a powdered nickel system, and apparently what the reaction is, I don't really know. I think copper appears in the sample afterwards. And a lot of this, he mentions a secret catalyst. I know of groups that have tried to reproduce Rossi's work, and they have not been successful. So there's probably something important that nobody knows, perhaps, except Rossi. And that makes it hard for other people to reproduce it. And I'm not saying Rossi's wrong. I can understand his reasoning, because if he has this commercial product, he has to get some patent protection. He needs some kind of protection. He can't just tell people everything. I have a recent patent on a battery, a lithium-air battery, that could be important. People tell me that a patent is not worth much if you can't get a lot of money behind it, a big company, because somebody else can copy it or come close to copying it. If they have a lot of money, they can defeat you in court, because unless you have a lot of money to fight it off, you probably would just give in. So I think Rossi's I don't know how much money he has, but he has to be careful what he reveals, because he could lose everything. He tells too much, and that's unfortunate that situation exists, but that's the way the world is. He can't tell everything. because he may have to fight this in patent court. He would rather get the commercial development done and have a device before he reveals everything that's needed to make it work. So I understand his position. It's a difficult position, and like I said, I hope he's right, and I hope we do get a commercial development by Rossi or somebody else in the near future, if possible.
Before we part ways, can you tell us more about any projects you're currently working on that people should be on the lookout for? I think you already mentioned a book that you're working on with Ruby. Maybe you can elaborate a bit.
Yeah, this book, I have all these letters from Martin Fleischmann, also some from Stan Pons, and I'm trying to collect them together. I haven't found them all. I had a lot of letters over the years, and I think this would give a lot of people insight into Martin Fleischmann's thinking and also his genius. So Martin Fleischmann is a true genius in his ability to mathematically model experiments and use mathematical equations. Nobody that I know of can match his ability in this area. And that'll show through in some of these letters. So I'm going to try to minimize the math as much as possible and just give the letters. I hope to get this out, sometime next year. I won't say when, but it's a big job. And Ruby is helping, like I mentioned, and we'll work on it as much as we can. So that's my main project for the coming year. I've been trying to get back on the Navy base, which is only 4 or 5 miles from here, but I haven't been able to do it. And there's people who want me to work with them on thermal batteries that I could work in their laboratory. If I get access to the laboratory, I would then have access to do cold fusion experiments. I almost have enough equipment here at home. I could actually do it at home, but I could do it much better at a Navy laboratory that have even better equipment available. And so I would do more experiments if I could get access to the Navy laboratory. That's my present position. But getting access without funding to Navy laboratories has become very difficult. So I'm not sure I'll be successful at doing that. But in the meantime, I'll work on the book and maybe a couple of more papers I'm thinking about writing. So that's what the near future that I plan on doing.
Well, that book project sounds very exciting. I know a lot of people that follow the cold fusion story, and especially the history of it, would be very interested to read those letters, because I think most of us that are listening to this think that both Fleischmann and Pons deserve an apology first and foremost, but their image deserves a rehabilitation. And Fleischmann and Pons before all this were really at the top of their games. And Fleischmann was a pioneer in his field. And again, true genius is the person that's willing to explore the unknown. He took this little hint from the 1920s of these guys that noticed some exotic behavior in Palladium-Deuterium systems. And they said, what the hell, let's go for it. And they might have discovered the greatest thing in the 21st century. I can't wait for that to come out, and I wish you all the best with that.
Yeah, I've always believed that eventually truth will win out. And I thought the truth about cold fusion would have won out long before now. And I'm not sure how many more years it'll take, but I think it will eventually win out, unless I'm wrong. But I think eventually the truth has to win. Maybe it takes new people. Maybe the old critics have to die off. Maybe it'll take new people to really make this truth really be recognized by the world. And so I think eventually Martin Fleischmann and Stan Pons will be vindicated. And the question is, how long is it going to take? To me, it's not a question of if, it's just a question of when this is going to happen. But I think in the future, sometime that will happen. But like I said, it's not the first time that a new idea had a lot of trouble getting accepted. James Prescott Joule, I've done some reading on him. You can look him up on Google, but he more or less came up with the first law of thermodynamics, relationship between heat and work. And his work was not accepted. It took a long time. He even told me, I even read that one time he was not allowed to participate in a scientific meeting and present his work, so he organized his own meeting and presented it in a church nearby in England because it wasn't accepted at that time. But his work is what led to the first law of thermodynamics. And so it's not the first time this has happened.
No.
But who knows how long it's going to take for indication. One other thing I have in mind of doing is I might write to the university chemistry departments and propose a seminar if they would invite me, if they'd allow me to come. And the title would be something along the lines of the impending vindication of Fleischmann and Pons in cold fusion. And by the title impending vindication, I think it will happen, and I think the universities need to know that. So if I find time later this year, next year, I might send out letters and see if I can get anybody to accept my coming and presenting a seminar on that topic at nearby universities, including possibly the University of Utah, where it all started.
Well, that would be truly excellent. One more parting story is Boltzmann and his kinetic theory of gases faced very similar obstacles. So something we take for granted now, the first law, Boltzmann's theory of gases, in its time and place, when it first came around, it seemed unbelievable. And then you give it another 50, 100 years and no one can conceive of it being any different. So as you mentioned, I think the genie's out of the bottle. I think it is only a matter of time. We can only do our part to keep the ball moving, and it gets taken up when it gets taken up, and I hope sooner than later. So Dr. Miles, thank you again for your time. This has been very informative, and you're a pioneer in this field. Thank you for all your work, and take care.
Okay, my pleasure, and I hope this helps. Cold fusion story helps to move it along.
All right, Dr. Miles, take care.
Okay, thank you.
So that does it for today's episode. Thanks again to Dr. Miles, Ruby Carrot over at coldfusionnow.org, and also thanks to you for listening. Take care and stay tuned for more episodes in the near future.